Okay, guys, good evening. Let's get
Good evening,
started.
sir.
Yeah, good evening. Are you all able to submit the assignment in time? I think its deadline is today, no? I don't know whether it is over or it is still open.
Most of the people are submitted, sir. I think so.
Submitted. Okay,
At
okay.
the end of the day, everybody will submit. From
Okay, okay. Good, good,
BMAT
good.
23 batch.
Sure, sure, sure. Excellent, good. So any questions going forward? Okay, maybe then let's get started. So we just started discussing the solution to system of nonlinear equations in the last lecture. So that is now, this is solution to system of nonlinear equations. Okay, so we said in general you will get systems of nonlinear equations in applications like CAD and in applications like chemical reactions and in the use of GPS, right? The global positioning system and several others in the solution of ODEs and PDEs. Okay, so in all of these applications, we're going to get systems of nonlinear equations. And then one way is to basically extend the Newton's method that we have learned, extends Newton's method to system of equations. Okay, so that means a natural extension of Newton's method exists, which can be used for solving systems of nonlinear equations. Now, in Newton's method, what we have done is we have basically linearized the nonlinear equations and solved them repeatedly. Okay, so that is the same strategy. The same strategy will be used to solve system of nonlinear equations. Okay, so we're going to essentially linearize all these equations, and then we're going to solve them in a repeated manner, in an iterative manner, to get to a solution. Okay, so fine. So what is an example of what is a general system of nonlinear equations? So to represent it, let me say we have one function f1 that is a function of there are several variables that could be x1, x2, x3, and so on, xn equal to 0. So that means we have several variables x1 to xn, and there is a function f1 that is in terms of these things. Okay, but then if we had only, I mean, earlier we just had function f of x equal to 0, where f of x is a nonlinear function, and whose roots we have found using different methods. Now we have, instead of just one variable, I have several variables. It could be x, y, z, and so on, but then it can be even more than that. So that's why I have used x1 to xn. Similarly, let us say we have another function f2, which is also a function of x1, x2, x3, and so on, xn equal to 0, right? And we have many such functions. And then the last function f of n is again a function of x1, x2, x3, and so on, xn equal to 0. Okay, so we have, that means we have n such functions. So we want to find the values of x1, x2, x3 such that they satisfy all these nonlinear functions at once. That means the solution is, what we are seeking is that we want to calculate what is this, all the values of x1, x2, x3, xn, such that they satisfy all these equations at the same time, right? That is the problem statement. That means if I were to represent all these values as some x bar equal to x1, x2, I mean x3 all the way to xn, right? Transpose, right? That means this is basically a column vector x1, x2, x3 all the way to xn, right? Then my equations are also can be written as a vector. That means f bar, which is a function of x bar, equal to 0, right? So this is the equation we are trying to solve, right, to obtain x bar. Okay, what is the x bar? Such that f bar of x bar equal to 0. Here by bar we mean that we are looking at a vector or several values. That means my f bar is equal to f1, f2, f3 all the way to fn, right? So if you want to write as a row vector, it's going to be f1, f2 all the way to fn transpose, right? Because these are all column vectors. So that is the question we are trying to solve. Okay, now that is the problem that we're trying to solve. Now let me kind of rewrite the general, essentially the Newton's method as we have learned. The Newton's method, what we have done is we have said x at n plus 1 equals xn minus f of xn divided by f prime xn, right? That's what we have said. We have basically said that the tangent is going to be a good approximation of the function in the neighborhood of the guess value, that is xn. And then wherever the tangent cuts the x-axis, we said that is the next best value for the root. And then we proceeded in the same way, right? And then we calculated from the new value of the root, we projected and calculated the f of xn, and we calculated xn plus 1, and then we repeated this process. Now, the same thing can be extended for system of nonlinear equation using Newton's method. Only thing is that instead of calculating xn, I'm now calculating xn bar n plus 1. Okay, so instead of n plus 1, let me write k plus 1. Okay, because n we are already making use for the length of the vector. Okay, so let me say k plus 1 equals, so x bar of k plus 1 equals x bar of k minus, we will get f bar of x bar of k. So this is similar to what we have written here. Okay, but then instead of f prime xn being in the denominator, we're going to get f bar prime x bar k inverse. Okay, so that's going to be the equation, working equation for the system of nonlinear equations. Okay, so this may sound little complicated because I have used over bars everywhere, but then we will derive this formula so that we can understand this better. Okay, so how is it going to work? So let me take an example of maybe three variables, x1, x2, and x3. Okay, and then let me also say that we have three functions, that is f1, f2, and f3. Okay, that means I have f1. Yeah, questions? So I have f of x1, x2, x3 equals 0, f2 of x1, x2, x3 equals 0, and then f3 of x1, x2, x3 equals 0. Can I sign later? Can I sign later? Tomorrow? Yeah, later, 5 o'clock. Okay, so we have these three functions, f1 of x1, x2, x3 equal to 0, f2 of x1, x2 equal to 0, and then f3 is also a function of these three. Okay, now what we want to do is that I want to now, let us say, use just like before, I want to make use of Taylor series expansion, and I want to express what is f1 of x1 plus delta x1, x2 of delta x2 plus delta x2. Okay, x2 plus delta x2, x3 plus delta x3. That means earlier, remember, we had f of x plus delta x, right? There was only one variable, and then we were going by delta x increment, right? Now I have, let us say, three variables, x1, x2, x3, and I'm going in increments of delta x1, delta x2, delta x3 in each of these variables. That means it is more like x plus delta x, y plus delta y, and z plus delta z, right? That's what we are trying to write. Y plus delta y plus z plus delta z, right? That's what I'm trying to calculate here. Okay, so these are the three variables that we're trying to calculate. Okay, now so just like Taylor series expansion for a single variable, I'm doing a Taylor series expansion for multivariables, right? So we are doing Taylor series expansion in multiple variables. Okay, that means we are writing this as f1 of x1, x2, x3. Okay, that is basically my f of x plus. Now I want to write this as partial f1 by partial x1 times delta x1. Okay, that is for the first variable. Then we have partial f1 by partial x2 times delta x2 plus partial f1 by partial x3 delta x3 plus, of course, I'll have more variables which are basically partial f1 by partial x square delta x1 square by 2 factorial partial square f1 by partial x2 square, delta x2 square by 2 factorial, partial f1 square by partial x3 square, delta x3 by 2 factorial, and so on. And then many things else. In fact, I will also have mixed derivatives like partial f1 by partial x1 partial x2 times delta x1 delta x2 and so on, right? We will keep on having several such terms, right? But then what I'm saying is that we are not interested in these higher order terms, right? So we are neglecting these higher order terms, and we are only going to keep the first order terms, that is the first order derivatives. That means the only the f1 of x1, x2, x3 plus the first derivative is what we're going to keep. Everything else we are not going to keep because we are only interested in the tangent value, right? So we are interested in only f of x plus partial f partial x of delta x is what we're interested in. The remaining values we are not going to, we're going to neglect them, right? And then because they are higher order and then they are small. Now, similarly, I can also expand what is f2 about x1 plus delta x1, x2 plus delta x2, and then I can also write x3 plus delta x3 as f2 of x1, x2, x3 plus I will get, instead of partial f1 that I have used here, right? Instead of partial f1 I have used here, I'm going to get partial f2, and everything else being the same, I'm going to get partial f2 by partial x1, delta x1, partial f2 by partial x2, delta x2, partial f2 by partial x3, delta x3, plus we're going to get the higher order terms, okay, which I'm not writing. Similarly, I can also write the function f3 equals x1 at x1 plus delta x1, sorry, this should be comma, x2 plus delta x2, x3 plus delta x3 equals f3 of x1, x2, x3 plus partial f3 by partial x1, delta x1, partial f3 by partial x2, delta x2 plus partial f3 by partial x3, delta x3, and so on, right? So that's what we have written. Now that means I have expanded all these three functions f1, f2, f3 in terms of the base value that is calculated at x1, x2, x3 plus the first terms in the Taylor series expansion. That means I can also combine all these things. I can write the left hand side into one term saying f bar of x bar plus delta x bar, right? Basically, this is now a vector, right? I have combined all these three equations into just one equation, right? The first one, second one, third one, saying that this is basically f bar, meaning this is a column vector, right? Something like f1 of x1 plus delta x1, x2 plus delta x2, x3 plus delta x3. Similarly, f2 of the same values, f3 of the same values. That's what I have written. Similarly, I have also written all these three as x bar plus delta x bar, meaning this is x1 plus delta x1, x2 plus delta x2, and x3 plus delta x3. So that's what I have written. So on left hand side, I have now condensed it to f bar equals x bar plus delta x bar equals, on the right hand side, the first term is basically f1, f2, f3. So this is going to be f bar. Okay, this is going to be f bar, and then they are all evaluated at x1, x2, x3. So this is going to be f bar of x bar plus I have now, yes, you can see there are three terms in the first row, right? I have three terms here, I have three more terms here, and I have three more terms here. So I have total of 9 terms. But then one thing that is common is that they're all multiplied with or by delta x1, delta x2, delta x3. First term is multiplied with delta x1, second with delta x2, third with delta x3, right? So that's what I have. So that means I'm going to write all these three as, I'm going to write this basically as a column vector, right? Column vector is delta x1, delta x2, delta x3. That is the column vector I have. Okay. And then what would be the matrix here? So because delta x1 is multiplying, the first term is partial f1 by partial x1. Next is partial f1 by partial x2. Next is partial f1 by partial. That means for the first row, f1 is going to remain the constant, remain the same, and then the denominator is going to change from x1, x2, x3. So this is going to be partial f1 by partial x1, partial f1 by partial x2, partial f1 by partial x3. Okay. Then the second row is going to be partial f2 by partial x1, partial f2 by partial x2, and then partial x3. So the second row we have f2 fixed, partial x2, partial f2 by partial x3. Similarly, the last row is going to be partial f3 by partial x1, partial f3 by partial x2, and then f3 by x3. So this is going to be partial f3 by partial x1, partial f3 by partial x2, partial f3 by partial x3, right? So that is what is our system is going to look like, right? So then that means when you multiply this with this matrix with this vector, we're going to get the same values as I have in the right hand side here, okay? So that we all agree. That means I can now write this as, if I'm going to denote this thing as some Jacobian, okay, which is as J, which is partial f1 by partial x1, partial f1 by partial x2, partial f1 by partial x3, and partial f2 by partial x1, f2 by x2, f2 by x3, and then partial f3 by partial x1, f3 by x2, f3 by x3. Okay, so that's what we have. That is Jacobian. Then I can simplify this equation as f bar x bar plus delta x bar on the left hand side equals f bar x bar. That's what I have, plus j times delta x bar, right? So j is a matrix times delta x bar. Delta x bar is a vector, right? That's what I have here. So this is j times delta x bar. So this is the equation I got for my Taylor series expansion. Okay. So now this is very much like what I have got previously, where I have got as f of x plus delta x equals f of x plus we got essentially f of x plus partial f by partial x times delta x, right? So you can draw an analogy between this equation and the top equation. This equation is for a single function with a single variable, whereas the top equation is for a vector of equations with a vector of unknowns, right? So that's what we have. Now, what did we do in the case of Newton's method? We said if this is the function, we drew a tangent. We said that is the tangent. If that is the tangent, which is denoted as L of x, then if it is going to intersect here, then this is your next value, right? Which is f of x plus delta x. That is going to be equal to 0. And then we said we're going to calculate the function value there. So that means our that means on my left hand side, x plus delta x is let us say if this is going to be the root, right, or is going to be the best or the next best guess, right? This is going to be the next best guess value for the root. Then my function is supposed to be 0 there, right? That is what we said. So this is going to be 0 bar. That means my f bar of x bar plus delta x bar equal to 0 bar, which basically means that from here, my delta x bar times j times delta x bar equals minus f of f bar of x bar, right? That means my delta x bar equals j inverse or minus j inverse times f bar of x bar, right? So this is the delta x bar, which is the change in the value of these vector quantities. That means if I want to calculate what is my next value, that is xk plus 1 equals x of k plus delta x bar, right? So that is the next iterate value. That's going to be x of k plus delta x bar is going to be, I'm going to substitute for this delta x bar, this value. That's going to be minus j inverse times f bar of x bar of k, right? Because this was evaluated at the k bar, at the k. Okay. So that is my formula for Newton's method as applied to a system of equations. Okay. Now, what is this j inverse bar? We wrote j as partial f as this thing. That is, this is nothing but f bar prime of x k, right? All these things are evaluated at x bar equals x bar k, right? So this is f bar prime of x k. I can write like that, right? Because prime means it is derivative. So this is going to be derivative for each of the functions in each of the directions. So that's going to give you 3 by 3 for a 3 by 3 system, and then n by n for if there are n variables and n functions. Okay, so that means j equals, what we have is j equals f bar of prime of x bar of k. Okay, that means my j inverse is going to be f bar prime of x bar k inverse, right? I cannot write in the denominator just like the way I have written before. So my formula is going to be x of k plus 1 equals, or x bar of k plus 1 equals x bar of k I should write this as x bar of k, okay, equals x bar of k minus f bar of prime of x bar of k inverse times f bar of x bar of k, okay. So that is my final formula for Newton's method applied to a system of nonlinear equations, okay. Um, okay. Questions on this? So x bar k is the guess value. Then I'm going to compute what is x bar k plus 1 in the next iteration. Then once I have x bar k plus 1, I'm going to use that x bar k plus 1, that value, and then calculate what is x bar k plus 1 next time, and then calculate this, and then use the x bar k plus 1, calculate x bar k plus 2, and so on, and hopefully assume that, or under favorable conditions, this is going to converge to a root that is going to be some r bar. Okay, so it's going to converge to a particular root r bar. Okay, any questions so far?
Oh, not at this time, sir. Like we'll review and get back to you. Sir.
Okay, okay, fine. Yeah. So, okay, then let us look at what do we do. So let us look at solving a sample problem and then writing some pseudocode for this method. So before that, I want to make a point here that in practice, we will not calculate J inverse. Okay, in practice, we are not going to calculate J inverse because we know that calculating inverses are expensive, right? Inverses are expensive. So we're not going to calculate J inverse, but then how are we going to solve this problem? So instead of calculating delta x bar equals minus J inverse f bar xk, so that means if I were to rewrite, so instead of solving delta x bar equals minus J inverse f bar of x bar k, okay, we are going to solve. So instead of solving this, we're going to solve, use the J inverse on the left hand side. That means we're going to solve for J times delta x bar equals f bar of x bar k, right? Where J is, I already know, which is f bar of x bar k prime, right? Times delta x bar equals, okay, there is a minus, so there is a minus f bar of x bar k, okay? So we're going to solve for this, which is basically, what is this? This is basically, this is ax equals b, right? Because we have some f bar prime x bar k, which will give you the entire Jacobian matrix evaluated x bar k times delta x bar. This is the unknown. We want to calculate what is that change in x, y, z, x1, x2, x3 with known right hand side. F bar is function is known, x bar of k is known. So calculate f bar at x bar k. That's going to give you a vector of values. So this is going to be ax equals b. So you solve for that because that is much easier, much cheaper than actually calculating x equals a inverse b. So, okay, so we're going to solve this system, and then we're going to update what is x bar k plus 1 equals x bar k plus delta x bar. Okay. Otherwise, what we're going to do is that we're not going to keep this minus there. Rather, we're going to solve for f bar prime x bar k times delta x bar equals plus of x bar of k. And then we're going to subtract off this delta x bar while updating x bar k plus 1. Okay, so either we will use this one or the top one, depending on both are the same. Instead of including minus here, we're just including it in the next step. Okay, so this is what we do in practice. We are not going to invert the Jacobian matrix. Okay, fine. Let us look at an example problem. I may need your help, or I may be able to solve it with my calculator. Okay, so I got my calculator. Let us say the example problem is find the intersection points for the circle x square plus y square equals 2 with the hyperbola, that is x square minus y square equals 1. Okay, so we are given a hyperbola and we are given a circle. We need to calculate all the intersection points with or for an initial guess of x bar 0 equals 1 comma 1. Okay, so for this initial guess, we need to calculate the intersection point. So that means x square plus y square equals 2. We are given a circle. Okay, so we are given a circle, that is x square plus y square equals 2. And then we are given, so that is x square plus y square plus 2. That is this equation. And then we are given a hyperbola. Let us say that is x square minus y square equals 1. So let us say that maybe looks like this. So we are asked to calculate what is the intersection points. Of course, there will be, in this case, there are 4 intersection points, but we are only given one initial guess, okay, which is basically your 1 comma 1 will be somewhere here. Okay, that is the initial guess we are given. Fine. So how do we solve this problem? This is going to be essentially first function is f1 of x comma y, right? Instead of x1 x2, I have x comma y. This is going to be x square plus y square equals 2. I'm going to write this as minus 2 equals 0. So that is my f1 of xy equals 0, which is a quadratic equation, which is a nonlinear equation. Similarly, my second function f2 of xy equals x square minus y square equals 1. So I bring it to left hand side. It's going to be minus 1, okay, equal to 0. So this is my first function. This is my second function. All right. And then the initial guess is given x bar 0 equals 1 comma 1. Okay, so we are starting from there. And then we are supposed to calculate one of the roots. That means, let us say we start from 1 comma 1, and then we have to calculate one of these roots of these intersections. Okay. Okay, how do we go about this thing? So we have this, so that we know that the formula for Newton's method or for a system of nonlinear equations is x bar k plus 1 equals x bar k plus delta x bar, where delta x bar is obtained from f bar prime x bar k times delta x bar equals minus f bar x bar k. Okay, so you see that both the function f bar and then the f bar prime are evaluated x bar k. Okay, so they are all evaluated x bar k. So that means when you are starting off from 0, these are evaluated x bar 0, right? That is the initial guess, and then later on at x bar 1 and so on, right? That is the process which we are going to follow. Okay, fine. So what is so then I already know what is x bar k. X bar k is 1 comma 1. Now I need to calculate what is f bar of x bar k. Okay, f bar of x bar k is going to be, I'm going to substitute for 1 comma 1 in this equation. So f bar of x bar of 0 is going to be substitute for 1 comma 1 in this thing. So it's going to be 1 plus 1 square plus 1 square minus 2. That's going to be 0. Then I have 1 square minus 1 square minus 1. So this is going to be minus 1. So that is my f bar of x bar of 0. Then I have to formulate what is f bar prime x bar k. That means first I have to calculate what is f bar prime. Then I can substitute it at x bar k. Okay. So how do I calculate f bar prime? F bar prime is nothing but, so f bar prime at x bar equals partial f1 by partial x, partial f1 by partial y, partial f2 by partial x, partial f2 by partial y. This is exactly same as what we had before. I just wrote in terms of xy instead of x1 y1, x1 x2. Okay, so then we have x square plus y square minus 2. So this is going to be so let me write it here. f1 of xy equals x square minus x square plus y square minus 2 equals 0. f2 of xy equals x square minus y square minus 1 equals 0. Okay, that's what we have. So this is going to be partial f1 by partial x is 2x, y is 2y, partial f2 by partial x is again 2x, partial f2 by partial y is going to be minus 2y. Okay, so that's what we have. But then this is still in terms of x and y. So we know that this is basically the general formula. So we can reuse this Jacobian matrix for calculating different xk values. But then now I'm going to evaluate this thing f bar of x bar of 0. That means in this f bar of x bar, I'm going to substitute for x bar 0 values, which is nothing but 0, 1. That's going to give me 0, 1, 1, right? My initial guess is 1, 1. X bar 0 is 1, 1. 0, minus 1 was my function value. So I'm going to substitute for 1, 1. It's going to give me 2, 2, 2, and minus 2. Okay, so that's what I have. Then to solve for this system, now I have everything. I have the left hand side, I have the right hand side. I can solve for what is delta x bar. That means I am going to solve for f bar of x bar 0. So let me write this as iteration 1. Okay, so this is iteration 1, which is going to be f bar of x bar 0 times delta x bar equals f bar of x bar 0. So you realize I'm not using a minus here, I'm using a plus. So I'm going to use, when I calculate x bar of k plus 1, I'm going to write x bar of k minus delta x bar. Okay, so I'm going to use it there. Fine. So then this system is going to be 2, 2, 2 minus 2. Okay, times this is going to be delta x, delta y, that is the function. On the right hand side, we have 0, minus 1, right? That's what we have obtained as 0, minus 1. Okay, fine. So that is what we have. Okay. Then how do I solve this problem? Maybe it's basically similar to your Gaussian elimination you have done before. Then row 2, we can say row 2 goes to row 2 minus, M21 is basically 1 minus row 1, right? That I can say. That means it's going to be 2, 2, and then we have 0, okay, times delta x, delta y equals, okay, this is going to be 2 minus 2, that is 0, minus 2, that is minus 4, and then minus 1, this is going to be minus 1. Okay, then I can use back substitution. This is not nice. Okay, so this is delta x, delta y. Okay, so that means delta y equals minus 1 divided by minus 4, that is 1 by 4. And then 2 delta x plus 2 delta y equals 0. That means delta x equals minus delta y. That means delta x equals minus 1 by 4, right? That means my delta x bar equals minus 1 by 4 and then 1 by 4. Okay, that is what I obtained by solving f bar x bar 0 delta x bar equals f bar of x bar 0. That means now I can calculate what is xk plus 1, that is x bar 1 equals x bar 0 minus delta x bar, right? Because in the calculations here I have not used a minus on the right hand side. So as a result, I'm writing it here. So this is going to be initial guess is given as 1, 1, and then my final answer is minus 1 by 4, 1 by 4. So this is basically going to give me 1 plus 1 by 4, that is 5 by 4, 1 minus 1 by 4, that is 3 by 4. Okay, so that is my x bar of 1. Okay, that is x bar of 1. Now let me do one more iteration. This is iteration number 2. Iteration number 2 is going to be again calculate f bar prime of x bar 1 times, right? This is x bar 1 times delta x bar equals f bar x bar 1. Okay, so that is going to be my f bar prime x bar was obtained as 2x, 2y, 2x minus 2y. Okay, substitute, evaluate this at 5 by 4 and 3 by 4 times delta x, delta y equals, on the right hand side, I need to now calculate what is x bar, f bar of x bar 1. So this is given as f1 equals x square plus y square minus 2 equals 0. And then f2 equals f1 equals x square minus y square by 2. And then f2 equals x square minus y square minus 1, right? X square plus y square minus 2. Okay, and then x square minus y square minus 1. Okay, that's what we're given. Okay, then I can substitute for x bar 1 in this thing. So that is going to be 5 by 4 and 3 by 4. So this is going to be, my f1 is going to be 5 by 4 is 25 by 16 plus 3 by 4 is 9 by 16 minus 2. 2 is going to be 32 by 16, right? Then my f1 equals 16. This is going to be 34, 25 plus 9, 34 minus 32. This is 2 by 16, that is 1 by 8. So this is 1 by 8. And my f2 is going to be x square is again 25 by 16 minus y square is 9 by 16 minus 1, that is 16 by 16. So this is going to be 25 minus 9, 16, 16 minus 16, 0. This is going to be 0. So this is 1 by 8 comma 0. Okay. So now, of course, I have to now substitute for x and y in the left hand side. So this is going to give me 2 times 5 by 4, that is 5 by 2, and then 2 times 3 by 4, that is 3 by 2. Then this is going to be 5 by 2 minus 3 by 2 times delta x delta y equals 1 by 8 comma 0. Okay, so that's what we have. Then again, I have to apply Gaussian elimination. That's going to be R2 tends to R2 minus R1, just like before. So this is going to be 5 by 2, 3 by 2, 1 by 8. So 5 by 2 minus 5 by 2, 0, minus 3 by 2 minus 3 by 2, that is going to be minus 3 times delta x delta y equal to, on the right hand side, I have 1 by 8, and this is going to be 0 minus 1 by 8 is going to be minus 1 by 8. Okay, that means my delta y is going to be 3 times delta y equals 1 by 8. So delta y equals 3 by, it's going to be 1 by 24, 1 by 24, and then 5 by 2 delta x plus 3 by 2 delta y equals 1 by 8. That means my delta x equals, so 5 by 2 delta x equals 1 by 8 minus 3 by 2, 1 by 24. So my delta x equals, how much will this be? Okay, let me just use calculator. So this is 1 divided by 8. This is 0.125 minus 3 divided by 48. Okay, this is minus 0.0625, 0.125. It's answer. So this is 0.0625. That means my delta x is going to be into 2 divided by 5. That is 0.025. So that is delta x. And then delta y was 1 by 8 would be 0.0125, is it? 0.125, not 0. Yeah. This is just 0.125, 0.25 by 2. Okay. So that means I got delta x delta y as 0.025, 0.125. Okay. That means I can calculate what is my x bar 2, that is equal to x bar 1 minus delta x bar. X bar 1 we have obtained as what? X bar 1 we have obtained as 5 by 4, 3 by 4. That is 5 by 4 is 1.25, 3 by 4 is 0.75, and then minus, we have now got 0.025, 0.125, right? If I were to calculate this, 1.25 minus 0.025 is 1.225, and then we have 0.75 minus 0.125 is 0.625. So you can repeat this process. You can repeat this process. And then eventually, hopefully, it will converge to some value of x bar, which is close to, I don't know exactly the answer. Let me check if I haven't written down anywhere. So it's going to probably converge to 1.2247 and then 0.7071. Okay, so it's going to converge to this one. That will be the exact answer, where your f bar of x bar of k in some norm will come out to be some value that is less than the tolerance. Now, of course, it only converts to one value because we started off with the initial guess as 1, 1. Okay, but then all other 4 values are going to be plus or minus these values. Okay, so that means if you start with 1 plus 1 or 1 minus 1, you're going to end up with another value. Similarly, if you start with minus 1, 1, you're going to end up with the other value, and then minus 1, minus 1 is going to give you the other value. That means depending on whatever is the initial guess you have taken, whether it is this one, this one, this one, or this one, you're going to end up with the corresponding closest root value, hopefully when it converges. Okay, so that is the idea. So that means, as you can see, in the case of nonlinear equations, we have multiple roots. It's not just a single root. Okay, there are multiple roots possible. So we have to see what is the root. Okay, even in the case of single equation, there are multiple roots, but in here it is actually even more so. And then we need to see which of the roots we are interested in, and then we have to give an initial guess closer to that root. Somehow we know the function behavior such that we'll be able to give a closer guess value. Okay. Okay, any questions so far? Is the methodology clear, what we try to do?
Yes, sir.
Okay, any
But it is
questions? Okay, fine, all right. So if you have any questions, feel free to ask me. Okay, then we have to write a subroutine for, function for calculating, the applying the solution of system of nonlinear equation using Newton method. So let me write that. That is going to be, let's say, some subroutine. This is Newton method for a system, and we are going to give the all the functions. We're going to give an initial guess, that is x bar. We are also going to give what are the number of iterations n max, and we're going to give what is the tolerance, right? So just like before, instead of giving f comma x, now we are giving f bar comma x bar. So here when we say f bar, we are giving the functional form, right? Somehow x square plus y square or something like that we are giving. And then, of course, we also need to give, so instead of n max, let me also write, okay, let me write, we are specifying the system size n, and then we are specifying x bar, f bar, and then let me use iteration max and epsilon, right? We have to give the size of the system. In this case, in the previous example problem, we have a 2x2 system. There are only x and y variable, and then there are two functions, or if it could be three variables in three functions and so on. Okay, and then so we have to specify the number of size of the system, and then the initial guess, and so on, all these things. Okay. So then what is the first step? The first step is, okay, again, we'll perform iterations. Do I equals 1 to iteration max. Okay, we'll perform a do loop. And then we're going to first calculate what is the function value. That means I'm going to calculate what is, let's say the x bar is the initial guess that is supplied. So I'm going to calculate what is f of, okay, I'm going to calculate what is f of 1 to n. Okay, so this is the f bar at x bar k, right? So we have x bar at x bar k. That is, I'm going to substitute for, in the f bar, I'm going to substitute for whatever is the initial guess. So here I'm going to substitute all the initial guesses, and then each of the functions is going to give me what is the value, right? So that's going to be one column vector, which I'm calling f of 1 to n. Okay, that is the column vector, and then f bar is the analytical expression, okay, for the functions. Could be like x square plus y square minus 2 and so on. Then I need to also calculate what is the Jacobian, right? The Jacobian is now a matrix that is of size 1 to n by 1 to n. That means I need to calculate what is the Jacobian quantities. These Jacobian quantities are essentially partial fi by partial xj, right? So my f bar is given. Then I'm going to differentiate. Let us say if I'm going to run, okay, I've used here let me use iterations. Okay, so let us say this is I, this is j direction. I is, let's say, rows, j is columns. Then I know that for the first row, my values are going to be partial f1 by partial x1, partial f1 by partial x2, and so on. So I'm going to somehow write all this in a particular loop, and then going to put in the j values in there. And then I have to evaluate what is the j value at that iteration. That means 1 to n, 1 to n. So once I calculate that, I'm going to evaluate what is j at that x bar, right? That is my x bar of 0, or x bar is I'm calling here. So I substitute for, in this expressions, this is similar to your 2x, 2y, 2x minus 2y, right? In this, I'm substituting for x bar of 0, that is 1 comma 1. Okay, then I'm going to get numerals for this Jacobian, and that is what I'm storing in the j here. Okay, so that's what I have done. So okay, so that means that I have now what is f, what is j. Then I can solve system of equations for solve system j times delta x bar equals f, right? So J is a matrix, f is a vector, delta x bar is my vector, right? So I can solve for this. Okay, so this is basically similar to solving f bar prime of x bar of k times delta x bar equals f bar of x bar k. Okay, that's what I'm trying to solve. So once I solve this thing, I know what is delta x bar. I know the correction. So this correction, right? Just give me 1 second. I'm going to switch off this. So once I know the correction, I'm going to update my values. That is x bar equals x bar minus delta x bar, because I have not used a minus in the previous step. I'm using a minus here. Okay. Then, so this is my new value. Now, if let's say my norm of the delta x bar is less than some tolerance, then I can say that essentially print the solution is converged. Okay, and then we can also print the value, that is x bar comma f bar, essentially the finalized value, and then we can return. Okay, if not, also we can print the iteration versus x bar, right? That's going to be the and then we can also, if we want, we can also print some value of f bar of x bar to get some norm. Okay, some 2 norm or infinite norm. Okay, and then we're going to say this is going to be and do, and this is going to be and subroutine the Newton method system. Okay, so that is the pseudo code for solving system of nonlinear equations using the Newton's method. Okay, any questions so far? Questions, mistakes? Okay, no questions. Fine. So let me let me look at an example problem. This I would like to give as, okay, we have done already the problem, but then I want to pose this thing. So in the case of GPS, I mean, all of you are using GPS, you know, whether to locate yourself on maps or whether to book some cab or something like that. How does this GPS thingy work? So essentially, we have a bunch of satellites, you know, which are, so we are on Earth. Let us say our Earth is something like that, a little bit. Okay. So then we have, you know, essentially, let us say we are on Earth here. Let us say we are somewhere here. Then we want to know, I mean, where we are, or we want to know where the cab is, right? All these things. So we want to essentially locate ourselves on this planet Earth. Okay, that means we want to calculate what is my position, and then again the position can be calculated either in terms of the Cartesian coordinates x, y, z, or it can be calculated in terms of the polar coordinates r, theta, phi, or spherical coordinates and so on, right? So let me stick to the Cartesian coordinates x, y, z. So this is my unknown, right? I want to know where I am on this planet Earth. Now then, what we do is that essentially we have several satellites, right? So we have, let us say we have a satellite that is going around the Earth, and then that is the satellite we have, which is going around the Earth at certain radius. Okay, typically the satellites are you know, at a height of typically about 20,900 kilometers. Okay, they are very, very far, right? About 20,000 kilometers from the surface of the Earth. But then essentially what you do is that you want to, let us say this is one satellite, this is satellite number 1. Okay. Then what you do is that you have to calculate x, y, z, but you know the position of the satellite. Let's say the satellite position is A1, B1, C1. Okay. Because we have launched it, we know its position at any given time. We know that because it's going around in an orbit that we have launched, we know that what is the exact location of the satellite, right? It is only going around the Earth. then essentially your handheld device, such as a phone or a GPS tracker, is going to send a signal, and that signal is going to reach the satellite, and it's going to come back, right? I mean, essentially, that is how you're going to then what you do is that you have, let's say, you can combine, so essentially you're sending a signal, and the signal is going from your handheld device to the satellite, okay? And then depending on how long does it take, the time it takes to reach the satellite, we can calculate the distance, right? The distance is basically the signals are traveling with, of course, not with speed of sound, because that is too slow. The signals are electromagnetic radiation, so they are traveling with speed of light, that is c. Okay, and then if it takes some time t1 to reach, then or to reach and come back, or just to reach, then this is going to be the distance between ourselves and the satellite. Okay, but then we also know that because this is the distance, this distance can also be written as using the distance between 2 points formula. That is going to be because a1, b1, c1 are known, and x, y, z is also known, so we can write this as x minus a1 square plus y minus b1 square plus z minus c1 square. So this is going to be the radius square, right? Because this is going around. Then the distance square is c times t1 square, right? Or c times c1 square. Okay, that's what we have. Or let me write c times t1 square is going to be that distance. Distance square is going to be this value. Okay, but then we have only one equation, right? Only one equation. But then what are the unknowns and knowns in this? So the known values are speed of light. We know how much time it takes. We can measure, right? You can, because you know what time you have sent, and then what time it has reached, and then it has come back. So either this equation can be made into 2 times what I have written. Okay. So we know that distance, and then we know the right hand side values. We also know what is a1, b1, c1. Okay, but then we don't know what is x, y, z. So we have only one equation, but then we have 3 unknowns, the coordinates of our position on the planet. So what do we do? Essentially, because we have 3 unknowns and we have only one equation, what people did was, okay, let us put more satellites. Okay, let's put another satellite which is going around the Earth, which is going to give me another whose position I know as A2, B2, C2. And then we can also say, okay, because I have 3 equations, this will only give me 2 equations. I need a third equation. So I'm going to put another satellite that is again going at some A3, B3, C3. So we have now essentially 3 equations. This is x minus a2 square plus y minus b2 square plus z minus c2 square equals c times t2 square. Okay, similarly x minus a3 square plus y minus b3 square plus z minus c3 square equals c times t3 square. Okay, so we have now 3 equations and 3 unknowns. So essentially this is a system of nonlinear equations. So it can be typically solved using your whatever the method we have learned, right? This is basically a system of nonlinear equations. We can solve for x, y, z from this set of equations. But then there is one problem. One problem is that although we can measure the time, the accuracy of the clocks in your phone or in the device and on the satellite are very different. Okay, the satellites are usually equipped with very accurate clocks, which are like atomic clocks, which are accurate up to 10 to the power minus 6 second, whereas your devices are not so accurate. So as a result, this small time difference, even though it is in microseconds, because of the speed of light and the distances involved, can cause a large difference in the can cause a large difference in the distance. Okay, calculation. So as a result, we may be, instead of at one place, we may be coming out at a different place. So as a result, this we need to subtract off what is the difference in time between the clocks. Okay, so let us say we call that as some d. So that is typically let us say subtracted off, and then we are using T1, T2, T3 because these satellite times need not be synchronized. So we know, and it can also reach at different times, right, from different satellites. So we are essentially subtracting off this d, but then we don't know what is the D value, right? This is the difference between the clock time and the satellite time. So, but then we have again now 3 equations and 4 unknowns, right? So how do we solve it? Solution is simple. Just put another satellite, right? If we have another unknown, just put another satellite. And then that's going to give you x minus a4 square plus y minus b4 square plus z minus c4 square equals ct4 minus d whole square, right? That's all. So once we solve for this, we will know the position x, y, z, and we'll also know what is the time difference, which can be used in calculating the x, y, z values. Okay, so we have 4 equations and 4 unknowns, which can be solved using system of nonlinear equations in Newton's method. That means your phone is always trying to solve this system of nonlinear equations every time you try to locate it using GPS. Okay, of course, now because we said the solution may or may not exist, in this case we don't want a no solution as an answer, because we want to know where we are located. So many a times people have developed or people have developed better algebraic solutions to this problem rather than using the system of nonlinear equation solutions as it is, to improve the reliability of the system. Okay, so but then I think this is a good example that we can say in the context of solving for system of nonlinear equations. Okay, I'm going to stop here, guys. We are out of time, and then I'll if you have any questions, you can ask me. Otherwise, I'll see you tomorrow at 4 o'clock. Okay, so we finished the solution to nonlinear equations chapter. So we will enter the next chapter, that is introduction to finite difference method. Okay.
Okay, sir. Thank you.
All right. Thank you, guys.
Thank you,
Thank
sir.
you, sir.
Thank you so much, sir.
Thank you. Thank you.
Thank
Thank
you,
you.
sir.
Thank you. Talk to you tomorrow.
Thank you.
Thank you.